Well, now that we have vector operators, we have the general definition, we have some specific examples. Let's see how we can combine vector operators to produce other things. Our first example would be rather trivial, at least sort of obvious. If V and W are two vector operators, that is V1, V2, V3 and W1, W2, W3 are vector operator components, then we define the dot product of V and W in the same way that we used to define dot products in, say, class 11. So V1 W1 plus V2 W2 plus V3 W3, and we expect this to be a scalar operator. Notice the only real difference here from the vectors that we dealt with in class 11 is that the components here are operators, so they don't necessarily commute. So we have to be careful not to mix up the order in which the operators appear. In V.W you always have V1 W1 plus V2 W2 plus V3 W3. In W.V you have W1 V1 plus W2 V2 plus W3 V3, and these two results may very well be different. But is it true that this is really a scalar operator? The proof of this is sort of trivial. You just figure out what happens when you take this V.W operator and rotate it, or rotate the coordinate, and what happens to the operator under that. And in, for all operators, it gets hit by u1 theta inverse on the left and u1 theta on the right. Of course, this V.W is nothing but this sum, and because these operators are linear, what we could do is simply move the u1 theta inverse in from the left, u1 theta in from the right, and more importantly, in between the Vi Wi in each term, I can put in this combination, which is of course the identity. So now we have two different pieces, the one in red on the left and one in blue on the right. One of them is u1 theta inverse Vi u1 theta, which you should recognize is nothing but Vi prime, the transformed Vi, and the part in blue is Wi prime. And what is Vi prime? Vi prime, we know, is nothing but a combination of Vj's dictated by Rn hat theta matrix elements. Being vector operators, V1, V2, V3 linearly combine the same way as coordinates do. So this has a Rn theta ij factor Vj summed over j. The same thing happens for Wi. There you have Rn theta ik Wk summed over k. We've just been careful to label these two summation indices differently. Now, of course, here what we are doing is we are summing up over j first to get Vi prime. We are summing up over k first to get Wi prime, and finally we are going to sum up over I. But since these are all finite sums, we could do them in any order we want, and we could sum up over I first, let's say, and then sum up over j and k. Of course, when we are summing over I, Vj and Wk can be moved out, always remembering to keep the relative order the same, and we can collect the Rn theta ij, Rn theta ik terms together, and this is what we get. Sum over I, Rn theta ij from here, Rn theta ik from here. Of course, these are just numbers, so they can happily jump over the operators Vj, and Vjwk is sitting on the right outside the I sum. Of course, that will sum up over j and k after that. Now, this sum should definitely remind you of a matrix multiplication, but notice that the summation index I is sitting in the first position for both of these. So, of course, this does not conform to the rules for matrix multiplication. I need this I to be a second index, and that's easy to do. All we have to do is take the transpose of the Rn hat theta matrix. Then this element is nothing but the jith element of the transpose, and jith element of the transpose times the ikth element of the original matrix summed over I is nothing but Rn hat theta transpose Rn hat theta's jkth element. Now comes the basic property of rotations. These matrices are orthogonal matrices, So Rn hat theta transpose Rn hat theta is nothing but the identity matrix, and its jkth element is nothing but the Kronecker delta jk. And finally we end up with this being the same as vjwj, which means it's the same as v dot w. So as promised, v dot w is a scalar operator. It does not change or transform when you rotate your coordinate system. Well, scalars are not the only things that you can get out of two vectors. You can actually get something more. You can form what is called an outer product and get tensors. So if v and w are vector operators, then the 9 operators t11, t12, t13 all the way up to t33, tij, formed by taking what is called the outer product vi wj. So v1 w1, then v1 w2 and so on. These form components of a tensor operator of rank 2. If you have studied Cartesian tensors, and I'm pretty sure most of you have studied it sometime or the other in mathematical physics, you would recognize that this is exactly how you form tensors of rank 2 out of vectors of rank 1 in ordinary tensor algebra. With operators, things are no different, except again you have to be careful of the order in which the operators appear in the product. So these 9 components transform, of course, to t prime ij, and t prime ij can be found from tij by hitting it on the left by un theta inverse and the right by un theta. But what exactly is the transformation rule? Well, since t hat ij is v hat I w hat j, this is what you get. And the same trick that we played a while ago, you can put in a un theta inverse in between the vi and wj, and you end up with this. The part in red here, of course, is the way vi transforms. The part in blue is the way wj transforms. So this is vi prime wj prime. And from the rules that we already have for vi prime and wj prime, vi prime is going to be this sum, wj prime is going to be this sum. But notice that here you have ik, here you have jl, as opposed to what you had in the previous case. There you had ik and il, and you also had a sum over I. Here you have no such sum over I, of course. So now you see that this is the way in which by just moving vkwl to the end, we realize that the transformation rule for tensor operators has to be Rn theta ik, Rn theta jl, tkl, and this is a generic transformation rule for any second rank tensor, or to be precise, we will call these second rank Cartesian tensors, because in the next lecture we will meet cousin of this, the spherical tensor. Well, the way tensor operators transform in general is this, and as you can see, tensor operators have two indices, I and j on this side and k and l on this side, and corresponding to each of the two indices you have two Rn hat theta factors. That's what makes them tensors of rank 2. Frankly, you can keep on going ahead with this. Tensors of rank 3 would have 3 indices, 3 Rn hat theta factors. So t hat ijk prime would change to a sum over a, b and c running from 1 to 3 of Rn hat theta ia, Rn hat theta jb, Rn hat theta kc, t hat abc. So after all, in a sense, this is nothing new. All we are saying is here you have 9 components for tensors of rank 3, of course 27, rank 4 81 and so on, which linearly combine according to a particular rule, and the linear combination factors in this case is made out of products of Rn hat theta components. Now this is exactly the same that happens for ordinary tensors where tensor components are numbers. So being operators makes no real difference here. The only difference, of course, is when you multiply them, you have to be careful of the order. And let me just clarify this once again. If you take the outer product of two operators, you get a tensor of rank 2, but that is the prototype of all tensors of rank 2. So any set of 9 operators which transform in this particular way will be a Cartesian tensor of rank 2. And as we have just stated, when you carry out a rotation of coordinates, the 9 components of a tensor operator, or these 9 operators which make up a tensor operator of rank 2, they combine linearly among each other. So they mix among each other. So if you form a vector space or a subspace of the set of all operators by taking all linear combinations of T11, T12, T13 up to T33, this linear space will be invariant under a rotation of coordinates because the resulting operator will be a member of this vector space again. So this is what we mean. They form an invariant linear subspace of the space of all operators which are acting on my system. But this is very important. This subspace is not irreducible. If you have forgotten what that means, let me remind you. These 9 components mix among each other, fine, but there are actually specific subspaces in this space of 9 basis vectors or 9-dimensional subspace, and these subspaces actually are invariant under rotations. What that means is you can look at specific linear combinations of these 9 operators which only mix among themselves and not with the rest. One rather easy to see thing is if you form an antisymmetric part by interchanging the ij indices. So this is a11 will be of course 0, t11 minus t11, but a12 will be t12 minus t21 divided by 2, and so on. And this of course gives you only 3 independent components, a12, a13 and a23. The others are either 0, a11, a22, a33 are 0, and a21 etc. are just nothing but negatives of the a12 version, and so on. So there are only 3 tensors which are antisymmetric. This is the antisymmetric part of the tensor Tij, and you can easily check that if you carry out a passive transformation, under that the antisymmetric part transforms among themselves. That is, the only a12, a13 and a23 only mix among themselves. They don't mix with the rest of the T components. Well, not only the antisymmetric part, even the symmetric part, which are 6 components, the other 6 formed by half Tij plus Tji. So S12, S13, S23 are there as before, and S21 etc. don't have to be counted again because they are the same as S12 and so on. We also have S11, S12, S13, S22 and S33 here, the diagonal terms. So these 6 components only mix among themselves when you rotate. Again, this has nothing to do with quantum mechanics and operators. This is a basic property of Cartesian tensors. The antisymmetric part of a second rank tensor stays antisymmetric under rotations, so they are just linear combinations of themselves. The symmetric part stays symmetric, so that's a linear combination of the symmetric components only. It so happens that even the 6-component or 6-dimensional symmetric part of subspace of this 9-dimensional space, even that is not invariant, and you already know that. Sorry, even that is not irreducible. You already know that because if you form the trace Tii, which for our direct product of Vi Wj would have been just V dot W sum over the 3 components V1 W1 plus V2 W2 plus V3 W3. This of course does not change when you rotate your coordinates, so it only mixes with itself, nothing else. So the trace is by itself forms a one-dimensional invariant subspace. The traceless symmetric part which you get, which is S bar hat, which you get from S hat ij by subtracting 1/3 of the trace. Why 1/3? Because there are 3 components. If you subtract 1/3 of the trace from each one of the diagonal elements, the resulting matrix will be traceless. So that is also invariant. The proof is trivial if you started with a traceless symmetric matrix, carried out the transformation. It should be easy to check that the result is a traceless symmetric matrix. So the traceless symmetric part of the matrix does not linearly combine with the trace part under rotation of coordinates. So ultimately, under rotation of coordinates, what you have is the 9 components that we had break up into a 1 component, which is the trace. I put in a 1/3 here so that you can write t hat ij directly in terms of this, plus 3 components of the antisymmetric part, plus 5 components of the symmetric traceless part. Of course, there are 6 independent components of a symmetric part, but the traceless restriction reduces 1 independent component. That is, the 3 diagonal elements are no longer independent. If you know 2 of them, the other one is obviously negative of the sum of the 2. So this is 5 components. So 9 components break into 1 plus 3 plus 5. Remember, we got to the second rank tensors by forming direct product of 2 vectors, 3 components each. So the count is fine. You had 3 times 3, 9 independent components to begin with, and now you have 1 plus 3 plus 5. Now, does 3 times 3 equal to 1 plus 3 plus 5 seem familiar? Except, of course, from what we learned in elementary school when you were a kid. Well, if it does not seem too familiar, let me remind you that 3 is the dimensionality of spin 1. So if you had 2 spin 1 systems and form the composite out of that, you would form a 9-dimensional space. But that composite space would break up into invariant subspaces under rotations characterized by the 3j values. So spin 1 and spin 1, when you add them together, you get spin 2, spin 1 and spin 0, which form 5-dimensional, 3-dimensional and 1-dimensional subspaces. So somehow that same pattern of decomposition of direct product subspaces which we learned while handling the Clebsch-Gordon expansion and so on seems to be making a comeback here. But these are of course very different things. These are operators. There we were talking of states and how they transform under rotations. So is there a reason why we are getting back the same pattern? Of course there is, and we are going to explore this further in the next lecture.